cosmological imprint of hot axions. Go ahead, Francesco.
Thank you. And can you see my screen and my pointer?
Yes, we see
Very
both
good.
of them.
Yeah, excellent. Thank you. Thank you. Good morning, everyone, or good afternoon, depending on where you are. And thank you very much for inviting me and giving me this opportunity to present my recent work on the cosmological imprints of hot axions. So my work and my talk will be about one particular axion. Now we speak about axion in broader terms, but I will refer to the QCD axion. The QCD axion is a motivated new degree of freedom beyond the standard model, motivated by the strong CP problem. So the strong CP problem is a serious puzzle in fundamental physics. We do not understand why strong interactions respect so well time reversal. Okay, so nature looks from the point of view of strong interaction invariant if we flip the arrow of time. And from the microscopic point of view, this corresponds to having a very, very small theta parameters, as small as 10 to the minus 10. Okay, so understanding this spectacular bound from experiments is the so-called strong CP problem, and the Paycheck-Quinn mechanism is not the only solution, but is one of the most elegant, if not the most elegant. So the basic ingredients of this solution are two, I would say: a new spontaneously broken symmetry, global symmetry, at some high scale FA. This FA is a dimension-full parameter, which is the scale of Paycheck-Quinn symmetry breaking. And in my plots, I will show a lot of results as they depend on FA. So FA is the so-called axion decay constant, and it's a scale where this new global symmetry is broken. And experimental bounds force this scale to be much higher than the weak scale, in particular, much higher than any energy we can reach in our labs. And a second important ingredient is that this symmetry is anomalous under strong interactions. So to be more quantitative, but not too much, at the scale FA, we have a spontaneous breaking of a symmetry, so we have a massless pseudo-Amorphous boson. But from the point of view of the anomaly, we also have this coupling here between the axion and the gluons. Anomalous coupling to other gauge bosons are possible, but they're not necessary to solve the strong CP problem. As we evolve the theory down, and here I have the electric phase transition, and here what it really matters for the strong CP problem, the QCD phase transition. This anomalous coupling generates a non-perturbative potential for the axion, which is not massless anymore, and as a mass which scales as the inverse of the axion decay constant. This number 10 to the 12 is a useful benchmark. So from this equation, you see that the axion is something very, very light. In particular, is something much lighter than the hypothetical dark matter candidates that we heard about in the previous talk. Okay, so we are definitely below the electron volt scale. So the axion, as I said, is motivated from the strong CP problem, but of course, another strong motivation for the axion is that the evolution, the cosmological evolution, is consistent with the fact that today axions account for the dark matter. So this is not the subject of my talk. The subject of my talk is hot axions, which I will define in a second. But cold axions, it's useful to remind how the scale FA, which is the axion decay constant, is connected to the requirement of achieving the correct Rayleigh density. So you see here on the horizontal axis, I have the scale FA. On this other horizontal axis, I have the axion mass. They are related, okay, from the equation I showed you before. And here on the vertical axis, I have the initial field value of the axion, which is a dimensionless variable, which is naturally expected to be of order 1, okay? But it doesn't have to be order 1. There are motivated scenarios where it's not order 1. So you see that whether the Paycheck-Quinn symmetry is broken after inflation or before inflation, but with the angle which is still around 1, the range of F that accounts for the correct Rayleigh density is at most 10 to the 11, let's say, okay? if I want the axion decay constant to be much larger, then I have to fine tune the initial angle, the initial value of the axion. Then there are, of course, motivation to do that. But I want to focus on this region. Okay, this is the region where the axion decay constant is not too small. And in particular, this is important because the axion couplings to standard model particles are proportional to the inverse axion decay constant. So in this region, the axion coupling to visible matter are larger. Okay, and so I want to investigate the cosmological consequences of this coupling to all standard model fields, potentially, because the axion, once you write down a UV completion, couples to the gluons with the coupling I showed you before, but it can couple also to the other gauge bosons and to fermions. And the cosmological consequences I want to explore are the so-called dark radiation or hot axions. So let me define what I mean by hot axions. By hot axions, I mean axions produced by processes involving particles from the thermal bath. These particles from the thermal bath can be standard model degrees of freedom, but it can also be new degrees of freedom. Imagine for example, a supersymmetric completion of the standard model. You can have also other particles in the thermal bath. And here I have just one example where BR, B1, B2, B3, these are generic degrees of freedom from the thermal bath. Okay, so B stands for bath here. And here I have a scattering process where there is one axion in the final state. This is just one example, could also be decays. Okay, it doesn't have to be all these scatterings. But what is important is that as a result of this collision, we have produced an axion which is much more energetic than its rest mass. Okay, so in this sense, they are hot. So imagine that these are standard model fermions. These processes happen when the fermions are in the bath. So the temperature of the bath has to be at least as large as the mass of these fermions. And the axion, remember, is way below the electron volt in mass. So this axion has a kinetic energy much, much larger than the rest mass. So this is a way to produce them. I will show examples how we produce this axion in the real universe, but then how do we detect their presence today in the universe? And the answer is through the cosmic CMB, the cosmic anisotropy spectrum, the CMB anisotropy spectrum. And in particular, they manifest themselves as an additional contribution to radiation. And from this equation here, I'm following the historical parameterization of this effect. This effect is parameterized as if there were additional neutrino species. Okay, so you see here there is this 7/8 from the statistics of the neutrinos. There is the ratio of the temperature, and then I have this ratio between the energy density of the axion divided by the one in photon. So what I want to do is to compute, to quantify this effect, and quantifying this effect corresponds to computing delta N effective from the axions. So here is a useful plot from a paper we wrote last summer, but there are other versions in the literature. Here we are considering, let's focus on the green line. Okay, the green line is for a scalar, so one internal degree of freedom, such as the axion. So here we have a particle which is originally in equilibrium with the bath, and it decouples at TD, which is a generic decoupling temperature. And here in this plot, I'm showing that as delta N effective depends on TD. Okay, so you see that even if they decouple as early as the electron weak phase transition, this effect is within the reach of future CMB stage 4 experiments. And at the moment, the bounds we have from Planck's are testing particles. In particular, I'm focusing here on the scalar because I want to talk about axions that decouple around the QCD phase transition. So this plot shows us that it's important to in order to have a careful prediction of delta N effective, it's important to investigate the decoupling carefully, because there is, if they decouple below the electroweak phase transition, as it will be the case for the examples I show in my talk, then there is a strong dependence on TD, because the thermal butt is losing degrees of freedom. It's a G-star effect, okay? So just estimating the decoupling temperature by imposing the rate equal to Hubble give us some feeling about the size of the effect, but if we want to make a precise prediction, we need to investigate decoupling carefully. Moreover, the axions may never thermalize, okay? Here in this plot, I'm assuming that this hypothetical degrees of freedom was in thermal equilibrium, but that doesn't have to be the case. So just to be very schematic, the way we quantify the effect is we solve the Boltzmann equation for the axions. On the right-hand side, there is, as usual, the effect of the collisions, and we compute the collisions just from particle physics. Given a specific model, we have coupling to the gauge bosons, not only the gluons, and we also have the coupling to the fermions. So there are different couplings in the game. Here, just a couple of papers that I work with my collaborators in the recent years. We investigated the effect of coupling to leptons. Here I only have muon or taus because decoupling to the electron is so constrained from stellar bounds that if you want to respect the stellar constraints, you don't make enough dark radiation. Okay, so that's why I only have the mu and the tau. And a more recent paper that we did roughly 1 year ago involves quarks from the third generation. And this is something that it was not too difficult to treat because the mass of the bottom and the top one are larger than the QCD phase transition, larger enough that we can ignore confinement once we make predictions for the delta and effective from the axiom. So I will not discuss this paper further because I want to discuss more recent stuff, but just the punchline of these two papers. If we have coupling to the leptons, we can alleviate the Hubble tension. In this paper, we did a careful analysis of the Planck data, and we found that the tension is alleviated but not solved. And concerning the third generation quarks, we quantify the effect of axion production via top and via bottom. In particular, once we consider the top, we did a smooth treatment of the electroweak phase transition because we have the confined and the confined phase. So we have rates. We computed the rates in the two opposite regime. We connected them at the transition. We produce smooth results and smooth predictions. And we found that these couplings are within the reach of a future CMB stage 4 surveys. What I want to talk about today are these two papers that we finalized over the last summer. And these involved also coupling to the first two generations and coupling to gluons. Once we couple to the lighter quarks and the gluons, and we know that the axion actually has to couple to the gluons, because if we are talking about the QCD axion, we need to couple to the gluons if we want to solve the strong CP problem. Then we need to face the QCD phase transition. And so I will tell you how we approach this problem in these two publications that I did in collaboration with my two postdocs, Joachim and Yun, that work with me in Padova. Okay, so let's start from the coupling to the gluons. As I said, this coupling is present in any model of the QCD axion. By QCD axion, I mean the axion solving the strong CP problem. And you know, if F is large enough that this operator decouples the axion before the QCD phase transition, then we can work in the deconfined phase. And it's not easy, but we can do that, and it has been done. Okay. This has been done in this series of paper, and the story was concluded in this last one here. And the problem is not easy to treat because the axion production goes through gluons. The gluons mediate long-range interactions. There are IR divergences that have to be regulated by a proper thermal field theory treatment. This has been done in a conclusive analysis was given in this paper here. And this is valid only above the QCD phase transition. You see that we have axion production through gluon and quark scatterings, all mediated by this single operator. If F is large enough, then the effect decouples above the GeV scale, and this analysis here is enough. But what if f gets smaller? If f gets smaller, then we approach the QCD phase transition where this operator is effective. Now, let's assume that f is small enough that actually the axion is still in thermal equilibrium once we are in the confined phase with pions, with hadrons. So, here we have the result from this analysis that for a specific UV completion, the so-called KSVZ axion, they provided the rate for axion production through pion scatterings. And a recent work from 1 year ago, roughly, showed that this calculation from the KPT point of view, from the point of view of current perturbation theory, is under control only for values of the temperature, roughly speaking, below 60 MeV. Okay, so in these two extremes, we have that the calculations has been done, and we have reliable predictions. Now, what if we want to provide a smooth connection between these two regimes and provide a smooth prediction for delta N effective? As I will show you, the values of f, which makes this relevant, are actually such that a smooth treatment is necessary. Let's go back to this paper from 2013, and let's look at the axion production rate via the gluon operator. The axion production rate via the gluon operator was studied here, and on the vertical axis, there is the axion production rate normalized by some power of the temperature and the axion decay constant, okay? Without going into details, I want to emphasize the horizontal axis of this result. This calculation was done only for temperatures above 10 to the 4 GeV. This is a region where you can completely forget about fermion masses. All the fermions in the standard model, you are in the electroweak symmetric phase, okay? So if we want to connect to the GeV scale, we need to fill this gap here on the left of this plot, okay? Moreover, something else that I would like to emphasize is that this result extrapolates the dimension 5 operator up to 10 to the 12 GeV. And this is not true in general in UV completions of the axion, because the contact interaction between the axion and the gluons is only valid once we consider energy scales below the mass of the fermion, which carries PQ charge and is colored. In the DFSZ axion, for example, this is true only below the weak scale, okay, because only the standard model fermions have a P-check-in charge. For the KSVZ is a model-dependent parameter, okay? So we fix both of these issues at the low temperature and the high temperature. So let me show you our result. This is the prediction for the axion rate, again, normalized by some power of the axion decay constant, just to show the results in a convenient way. As a function of the temperature, you see that on the left part of this plot, you have the pion theory. On the right, you have the gluon and quark theory. And this black line is a new calculation that we did, because the previous slide was only valid above 10 to the 4 GeV. Here, we pushed that down below as low as 2 GeV. And in order to do this, we had to introduce fermion masses, do a proper field theory calculations, integrating out the fermions and the threshold, and so on. In this intermediate regime, we connected the rates with the smooth interpolation, and we put two values of the threshold when the pion theory fails. The first one is the 62 MeV, which I mentioned in the previous slide from KPT perturbation theory breakdown. And here is 150 MeV, where the hadron gas approximation is, hadron resonance gas approximation breaks down. You see that it doesn't really matter. There is a zoom here where you match. Of course, we are aware that there are lots of, there is a lot of stuff in this region, but eventually you have to take cross sections, you have to take thermal averages, and you have to solve the Boltzmann equation. So all resonance effect here gets smeared out by these effects. And if you want, I can also tell you more about the error that we estimated in doing this interpolation. Okay, so let me go now to a couple of results for illustration. We consider the KSVZ axiom. The KSVZ is summarized in this slide. The energy, there is the Pecha-Quinn symmetry breaking is here, and the anomaly is ensured by this heavy color fermion psi, which gets mass after Pecha-Quinn breaking. And then eventually at the low energy scale, once we integrate out these heavy fermions psi, we end up with the axion coupling to gluons. So this is the model where in the high energy, the axion couples only to gluons, okay? Only to the GG dual operator. And here is the result. So this is the first time I show you a prediction for delta and effective. So let me show you the way we decided to present our results. Delta and effective on the vertical axis. These horizontal bands are current bounds, future bounds, and then the axion decay constant here, Fa, and the axion mass here. Okay. The gray region is shaded because it's excluded by stellar bounds, these supernova bounds. And the different lines corresponds to different initial condition for the axion field evolution, for the axion density, number density evolution. And here we fix the mass of the heavy fermion to 10 to the 5 GeV. So in the plot, previous plot, this plot here that I mentioned that this result was extrapolated up to here, we fix this issue, okay? If the mass of the heavy fermion is 10 to the 5, then you should not trust this plot on the right of 10 to the 5, because there is no dimension 5 operator, contact interaction with gluons anymore. So we fix that, and we see that as we consider, we set the initial axion density to 0, because we want to quantify these axions produced in the IR. And if the temperature is larger than the mass of this fermion, then the prediction is not sensitive to the mass of the fermion anymore. Because the theory above the mass of the fermion, the interaction producing the axions are renormalizable. So you have some IR sensitivity analogous to the one you have for dark matter freezing. Of course, if you start later, then you make less axion, but eventually all of these lines connect to a smooth, to a single prediction, because if you thermalize that, you raise memory of what happened before. And you see from this plot that future CMB stage 4 experiments will be able to test the KSVZ axion in this region slightly above the stellar bounds, the supernova bounds. We did the same for the DFSZ axion. DFSZ axion, again, a quick summary here. You have you extend the X sector by 2X doublets. You don't have any new fermion, so the anomaly is ensured by standard model fermions, standard model quarks in particular, the QCD anomaly. And now in the infrared, you have a more complicated theory because you couple not only to gluons, but you also couple to other gauge bosons, and you couple also to fermions. Here, for completeness, I also put the coupling to the X, but it's redundant. You can really find that away. And here is the analogous plot for the DFSZ axion, where again, we fix the mass. Now, the heavy physics is the CP of the scalar in the 2X doublet model. We fix the value of tan beta for illustration. We also explore the dependence on tan beta. It's not so important. And here we see that there are two different bounds for the DFS, one for the supernova, one for white dwarfs. The reason why there is one more bound here is that the DFSZ axion couples also to electrons. Okay, so you have also a stronger stellar constraint, and you see here that future CMB stage 4 experiments can barely test the region which is not excluded by stellar bounds. And these are the two most famous realization of the Pecha-Quinn mechanism, the KSVZ and the DFSZ. But of course, our machinery can be applied to any other UV completion for the axion that if you want to connect the two phases before and after confinement. In the last minutes that I have available, I would like also to mention this more recent work that was completed last November, this time with Seokun Yoon, which was one of my two collaborators in the previous projects. And this time we investigated flavor violating couplings. Okay, so everything I said so far for the axion is for flavor conserving couplings. Okay, so the axion couples to two fermions, and these two fermions are the same fermion. Okay, there is no communication among generations besides the one that are suppressed by CKM factors, and we checked that there is no impact on cosmology for these CKM suppressed couplings. Okay, so in this first paper, we took a very pragmatic approach. We didn't specify any UV completion, and we consider the most general theory where the axion here couples through, as usual, Fa suppressed interactions, dimension 5, but now couples to fermions via flavor violating operators. So you see that in this sum, I'm not considering the same coupling, I'm considering two different flavors. One example could be the bottom and the strange, okay? And these couplings are the target of several terrestrial experiments because they can mediate rare meson decays and so on. And there is a lot of activity on quantifying bounds from current experiments on these couplings, as well as predicting what future experiments, future kaon factories or analogous experiments can test, in particular, what values of F over C can be excluded by these experiments. And so what we did in this paper, we worried about their role in the early universe. And of course, the story is analogous to the previous one I told you. They can mediate hot axion production, the production of axions that are relativistic. And one obvious production channel is through decays, okay? Because if I have, for example, a bottom here and a strange here, I can have the bottom decaying to the strange and the axion. But something that was not considered before our work for this flavor violating coupling was that you can also have production via scatterings. For example, you attach to this quark leg one other quark and a gluon, and this vertex is enhanced by alpha strong. Okay, so we found that production via scatterings in some cases, especially for quarks such as the bottom and the charm, so we are considering production not too far from the GeV scale, scatterings can dominate the production. So just to give you a quick overview of our finding, we decided to present our results in this way. This is standard from flavor violating axions publications on terrestrial experiments. What we did was to add these green bands. Okay, so the darker bands are current bounds, fainter bands are future prospects. So for example, here I have the coupling between the tau and the electron, vector or axial, it doesn't matter. This orange band is what is excluded, and I'm using as conventional in the literature this variable here, capital F, which is 2 lowercase f divided by C. And this fainter band is what can be tested in the future. So you see that the role of cosmology is actually quite important. For example, for this tau coupling, cosmology is already doing better than experiments from Earth. And in the future, here, these two fainter band, we put both the projection 1 sigma and 2 sigma. You see that they're going to be much better than the terrestrial experiments. For the hadronic flavor violation, once the axion coupled to quarks, the story is analogous. We did systematic classifications of all couplings. You see SD, SD, CEU, all possible combination. And again, you see that cosmology has always something to say. Now, for coupling to the bottom, actually, the reach is only if we consider the discovery reach at 1 sigma. But if we go, for example, to strange or charm, the CMB stage 4 are actually competitive with flavor experiments. So to summarize, this CMB data provide a complementary probe to these terrestrial experiments looking for flavor violating couplings. So to summarize what I told you today, the QCD axion, of course, is one of the best motivated particles beyond the standard model. It is motivated because it solves the strong CP problem, and it is motivated also because it provides one of the viable dark matter candidates. Remember this figure with the relevant axion range, axion decay constant range. What I told you about is that besides this population of cold axions accounting for dark matter, we expect to have also a population of hot axions analogous to the cosmic neutrino background. And the effect of this hot axion population is precisely the one of adding extra radiation once we look at the CMB spectrum. So these hot axions are complementary probes to the page-equi mechanism besides other axion searches on Earth, as well as to flavor violation, as I told you in the last 3 slides. And we are just considering right now other future work. For example, we only study these 2 popular UV completion for the axion, the KSV and the DFSZ. But of course, these are not the only models on the market. And in particular, we are exploring now flavor violating completion for the axion. What I showed you before in the previous slide was just one coupling switched on at a time. But we want to consider UV completion and see how the experimental bounds apply to UV completion. And if you want, you can also consider how these effects change if you consider modified cosmological history besides the one of radiation domination, the boring thermal bath I told you about. And also, there are axions in other UV completion and other motivated frameworks beyond the standard model, not only the QCD axions. So these CMB experiments can provide a motivated test for these hypothetical theories. So I stop here. I thank you for your attention, and I will be very happy to answer your question now.
Thank you very much, Francesco. Even though we have used all time, we'll take a short question if there is one.
I have a question.
Okay.
Hi, Francesco.
Hi, nice to see you.
Yeah. So you, as I remember, you took the initial action abundance to 0 at some high temperature, Ti, and so you varied over several values to show the N effective. And does it mean that your conclusion depends on the initial condition, or how can I understand your plot?
Okay, so let's discuss the KSVZ axion. So you mentioned this plot here.
Yes.
Okay, so what I did here was to assume that at some point in the expansion history, I have 0 abundance, and then I produce that below the temperature. Of course, this is something we don't know. Okay, imagine that you have reheating at 10 to the 4 GeV. Through the reheating process, you may as well have 0 axions if the infiltron doesn't decay to axions. Okay, so that's possible that you start from 0. Maybe I have a backup slide. Let me check if I have. Here, yes, this is the slide I wanted to show you. So I only show this case and ATI equal to 0 for simplicity. But in the paper, we actually show what happens if at some point you have to run your Boltzmann code. Okay, so what happens if at the initial time we impose the equilibrium abundance? And here is the band that you see. Because we vary this initial temperature on this range between 10 GeV and 10 to the 4 GeV. Then afterwards, it doesn't depend anymore. So to answer your question, if reheating is high enough and there is no action produced during the heating, then the line to look at is the red. But it's something intermediate between these two, and this is an ignorance that we have, and we were honest. We just consider all the extremes. You either have the equilibrium or you have zero, and
so before the action decoupled, I mean, before the action is decoupled, you assume that action to be in thermal equilibrium. But somehow you set the initial condition for the action abundance to zero.
yes,
right.
yes.
And once it is produced, it will be back in thermal equilibrium.
Yeah, exactly. So if you see if F is small enough in this region here,
right.
it doesn't depend too much on what happened before. If they thermalize, you erase memory of what happened before. But of course, if F is not small enough to thermalize, then you are sensitive to these initial conditions.
Okay.
Okay, yeah, nice discussion. Thank you very much, Francesco, for your talk. We'll move to the last speaker of this session, Keisuke Harigaya from CERN. He will talk about axion rotation. Keisuke, are you there?
Yes.
Hi.
Hi.
We can see your slide. We can hear you fine. Please go ahead.
Great. So thank you for the invitation to give a talk here. I'm Keisuke Harigaya from CERN. So today I would like to talk about my recent work on the cosmology of axion rotation based on this paper, mainly the first two papers. I also mentioned the other four papers in the meantime. So here's a brief summary of my presentation. Today I would like to present a new cosmological dynamics of the QCD axiom that explains dark matter for action coupling constant much larger than the prediction of the conventional action dark matter production mechanisms, creates a baryon asymmetry of the universe, and predicts parameters of new physics beyond the QCD axiom. So that's what I'm going to talk about. So here's a more concrete outline. I'll first give a brief introduction on the QCD axiom and the idea of the action dark matter. So then I will introduce the new dynamics, action rotation, and how that impacts the action dark matter abundance. So then I will then explain how the action rotation can give rise to the observed baryon asymmetry in the universe and associated predictions. And finally give a brief summary and a discussion. Okay, let's start from the introduction. So as Francesco said, QCD axiom is a very motivated extension of the standard model. It solves the strong CP problem dynamically and is a good dark matter candidate. So because of these motivations, so there has been many action research conducted and proposed, and there have been many cosmological considerations on the action, like Francesco did. But our question we should ask is, on which point in this parameter space, so the QCD action can be actually the dark matter of the universe. We know that the abundance of dark matter. So our question is, how can we populate the action dark matter of this abundance in the universe? Of course, there is a standard answer to this question. People consider sort of a misalignment mechanism. So action is right. So there's no reason that action field sit at the minimum of its potential, but generically it's displaced from the minimum by amount called the misalignment angle. And later, the action field begin oscillation around its minimum and behave as a dark matter. So in this scenario, we can compute the action abundance as a function of the initial misalignment angle and the unique parameter of the QCD axiom, namely the decay constant. And here is the formula for the action dark matter abundance. So you can see that if the misalignment angle is a natural one, order one, the decay constant around 10 to 12 GB is required. So let's overlay the prediction on the action search plot. So if the misalignment angle is all around, the prediction is around here. But if you fine tune the initial condition of the action field to be a small one, so the small action mass, or equivalently large decay constant, equivalently smaller coupling of the action is also consistent with the idea of action dark matter. In this conventional scenario, large action mass corresponding to large action coupling is inconsistent with the idea of action dark matter because action is underproduced as dark matter. So today I'd like to present new cosmological dynamics of QC action that enhances action dark matter abundance and predict a larger coupling and create barrier similar to the universe and have implication for action searches and new physics beyond the QCD action. Okay, so let me introduce that new dynamics, action rotation. So in the discussion so far, we have implicitly assumed that action is initially static. It has initial vanishing velocity and begin dynamics at later time. But let us consider an alternative possibility that action has non-zero initial velocity, namely non-zero kinetic energy. So I will later introduce how we can indeed set such an initial condition, but let us for now assume such an initial condition and discuss a phenomenological implication. What happened here would be that this action has extra energy, not only potential energy, but the kinetic energy. If this kinetic energy is transferred into the action dark matter density, we can enhance the action abundance. So we can call such a scenario kinetic misalignment. Now you can indeed see that action abundance will be enhanced. So here, let's solve the dynamics of QC action. The blue ball has a vanishing velocity and red ball has non-zero velocity. Okay, let's start the computation. So you can see that because of the initial non-zero velocity, so action oscillation around the minimum is delayed in comparison with a conventional scenario, and the action abundance is indeed enhanced. So we can make prediction a bit more precisely at the quantitative level. So when this action oscillation begins with this delay, the number of the action at that time is given by the mass of the action at that time, frequency times amplitude, decay constant square. When the oscillation begins, this action mass would be as large as the velocity of the action, so that action can be indeed trapped at this potential. So you can see that the number of acceleration would be as large as the angular velocity times the decay constant square. So this is nothing but the angular momentum of the rotation. So in other words, Pecha-Quinn charge density associated with the action rotation. So to sum in this mechanism, action number density is equal to the Pecha-Quinn charge. So with detailed study, it turned out actually this is not the correct picture, but because of this non-trivial cosine potential, actions are produced by parametric resonance, and that is the dominant source of the action dark matter. But it turns out that the action number density remain the same, namely action number density is as large as this is initial angular momentum density. So in this way, so we can enhance action dark matter density by if there were this initial huge velocity. So then this means that in the parameter region where the conventional mechanism underproduces action dark matter, this kinetic misalignment can populate enough amount of action dark matter, and we have implication to the action searches that are sensitive to the large action coupling, or some cosmological consideration like hot action that is sensitive to the large action coupling. This looks good, but the question is how can we prepare such a very special initial condition? But to do that, let us consider so-called the affect time mechanism originally considered to initiate the rotation of the super pattern of the quarks and leptons, lepton and leptons. So in addition to the dynamics of the angular direction, theta, let us consider the dynamics of the radial direction, s. So let us imagine that not only the angular direction, but the radial direction is displaced from the minimum in the early universe, like this. So here, red ball, the initial condition in the very early universe, and red one is a minimum. For such large field value, much larger than decay constant, so higher order terms in the potential can be important. So in particular, such higher order terms may contain the explicit Peychakin symmetry breaking terms. Such terms are indeed expected to be present in the theory where Peychakin symmetry is understood as an accidental symmetry, like an accidental baryon symmetry in the standard model. So with such a higher term that explicitly breaks the Peychakin symmetry and the large initial field value, the potential is no longer U1 symmetric at large field value, but has a potential gradient to the angular direction. But by the gradient to the angular direction, rotation is initiated like this. So then later, because of the cosmic expansion, radial field value decreases, and this explicit breaking term is no longer effective. So then this complex field continues to rotate, conserving the angular momentum. In field theory language, this is nothing but a nature charge associated with the Peychakin symmetry, and in our case correspond to the axial rotation. So this is nothing but the idea of the affect time mechanism to initiate the complex field in MSM, but we can just trivially apply that method to initiate axial rotation. There is one thing we should be slightly bit more careful. When this rotation is initiated, it's generally not a completely circular one, but it is a superposition of the angular mode, the rotation, and the radial mode, radial oscillation. What we want is this angular mode, but we do not want this radial mode because it will eventually dominate the universe and produce entropy and may dilute the angular momentum of the action field. So we must somehow dissipate the radial mode by coupling of the complex Peychakin symmetry breaking field to the thermal path. Then you may be worried that once we dissipate the radial motion, angular motion is also dissipated. So in particular, so we have that the Peychakin symmetry has a QCD anomaly. So there's a very good chance that the Peychakin charge is transferred into the co-chiral asymmetry via QCD spiral processes. But it turns out that the rotation is thermodynamically stable for the following reason. So to do that, let us just compare the chemical potential of the system and compute the number of asymmetries. This rotation has a chemical potential as large as the energy density of the rotation, namely kinetic energy, divided by the Peychakin charge. So this is just angular velocity of the rotation. Then once this particle antiparticle asymmetry in the thermal bath, like co-chiral asymmetry, is in thermal equilibrium with the rotation, they should also have the chemical potential as large as the angular velocity of the action field. So then now the charge in the rotation is as large as angular velocity times the radius square, namely decay constant square, while the charge in the bath would be as large as angular velocity, the chemical potential, times temperature square times the ordinal factor. And you can see that at the thermal equilibrium, where chemical potential equivalent, the charge in the rotation is much larger than the charge in the particle antiparticle asymmetry of the bath, as long as the decay constant is much larger than temperature. So despite the possible charge transfer from the rotation to the to the thermal burst associated with the dissipation of the radial mode, the rotation remains stable, and almost all charges are in the form of the rotation. So at the later part in the talk, I will use this result. The charge asymmetry of the burst as large as angular velocity times temperature squared. So please remember this formula. Okay, that's all about the kinetic misalignments. So I focus on the QC action, but we can apply this idea to generic action-like particle. So for the generic action-like particle, where mass and decay constant, our coupling constants are the independent free parameter, the gray region is a prediction from the conventional misalignment mechanism, where in the circled region, action is underproduced as dark matter. But again, if we apply this idea, kinetic misalignment mechanism to action-like particle, we can populate the action-like particle dark matter, even in this usually underproduced region. Okay, that's all about kinetic misalignment mechanism. So let me make connection of this dynamics with baryon asymmetry. So it turns out this rotation can also produce a baryon asymmetry via mechanism we call axiogenesis in the following way. So let's again start from the axial rotation that has non-zero page-Jacquin charge density. So we know that this page-Jacquin symmetry is quantum mechanically broken by the QC anomaly. And we expect, and what happens should be that in the R universe, QC's Pharon process destroy the page-Jacquin charge. But at the same time, the co-chiral symmetry also has a QCD anomaly. So then what happens is page-Jacquin charge is destroyed, but at the same time, co-chiral charge are produced. So the page-Jacquin charge is transferred into chiral asymmetry of particles or quarks. So then, if there exists some baryon number biorhythmic process, either from standard model, namely Weak's Pharon process, or beyond the standard model interaction, such as a minor neutron mass or R parity variation in supersymmetric theory, or any BSM that you like and contains baryon number vibration, this chiral charge can be transferred into baryon asymmetry of the universe. So in this type of scenario, the QC action can address three problems in the universe. Why does QC preserve CP symmetry, namely strong CP problem? What is the identity of dark matter, and how was the baryon asymmetry universe created in the early universe? So as I told you, baryon number variation could be anything, but today I mainly focus on the baryon number variation in the standard model, namely electric Pharon. So we call the axiogenesis based on this scenario, Maiman axiogenesis. I will explain this in detail. But we can also consider baryon number variation from beyond the standard model interaction you like. I will introduce them briefly later. Okay, let us first consider minimal axiogenesis. To recap, what happened is page-Jacquin charge is transferred into co-chiral charge via QC's Pharon process, and the co-chiral charge is transferred into baryon, actually B plus L asymmetry via the Weak's Pharon process. So because these are mediated by a sample process, this is really effective. And before the adequate phase transition, where Weak's Pharon process is effective, baryon number reaches the thermal equilibrium value as large as the formula given in the previous slide about order factor 0.1 times angular velocity of the action times temperature squared. And this baryon asymmetry is frozen upon the weak phase transition because electric process becomes exponentially suppressed. So baryon number is conserved afterwards. So we should estimate the baryon asymmetry at the electric phase transition. So in this scenario, there are three free parameters: angular velocity axiom, decay constant QC axiom, and generically electric phase transition temperature. Of course, assuming standard model, the third one is fixed, but let us for now treat it as a free parameter and use immediately see the reason why I should do that. And then from those three parameters, we should explain two observed density, dark matter and baryon density. So 3 minus 2 equal 1. So we end up with a 1 free parameter. If we choose that to be the decay constant, we can predict the required liquefaction temperature, and the formula turned out to be given by this. Unfortunately, given the astrophysical lower bound, supernova bound of the decay constant about 10 to 8 GeV, the liquefaction temperature of 100 GeV is inconsistent with the scenario. But however, once we consider BSM scenario where the liquefaction temperature can be larger, we can provide the connection between the QC action physics, namely decay constant, and the parameter in the extension of the electric physics. So it will be interesting to check the conical scenario where some new particle couples to the Higgs and indeed change the liquefaction temperature, maybe create a possible collider signal of such scenario with the QC action decay constant. So we can apply the same idea to the generic action-like particles. Again, the rotation in the action-like particle can be transferred into baryon asymmetry via the Weak's baryon and action-sum model couplings. So in this scenario, we have three parameters. Let's take three parameters: angular velocity, decay constant, and the action-like particle. And let's now fix the electric phase transition temperature to be a standard 100 GeV. So in the 3 minus 2 equal 1, we have one free parameter. So we can now predict the decay constant of the action-like particle as a function of the mass of the action-like particles. The formula is given here. And such a prediction is shown as this green band, which we call the prediction of the ARP cogenesis. So here, to make prediction of action-like particle and photon coupling, we assume the natural relation between a decay constant and an ARP photon coupling, namely loop separation by times 1/f. You can see that the prediction is much larger than that of the QC action, and that is the misalignment mechanism for action-like particle dark matter. So I would like to present this as a possible benchmark point for action studies in various experiments. And you can see that indeed many experiments cover these predictions. So far, we concentrated on the baryon variation from the standard model, but we can of course combine this scenario with baryon variation from BSM, like minor neutron mass, R parity variation in superstring theory, anything what you like. So again, in this scenario, we can make connection between QC reaction and other physics. So generally, we have three types of parameters. So angular velocity, decay constant. Assuming QC reaction, there's action must be predicted as a function of decay constant. And also BSM parameters that is responsible for the baryon number variation, and from which we should explain two. So we now obtain one relation among beyond standard parameters and the QC action decay constant, and make connection between BSM physics and the QC action physics. So here I briefly list what I have considered. So we can consider the B-L variation from minor neutron mass. And it turns out that the mass of the radial direction of the Pechak symmetry breaking field is predicted. So if we embed this scenario into the supersymmetric theory, mass of the radial direction of the Pechak symmetry breaking field can be connected with a supersymmetry breaking scale. So we can make prediction on the SUJI scale in this scenario. Speaking of SUJI, so we can consider baryon number variation in supersymmetry models called the R parity variation. So in this scenario, magnitude of the R parity variation and scalar masses are predicted as a function of the QC action decay constant. So for under certain assumptions, this predicts the proton decay rate as a function of the decay constant and scalar masses in SUJI theory. Well, we can utilize foreign processes in new gauge interaction beyond the standard model. So then we can make a prediction of the mass of new gauge boson as a function of the decay constant. So this is the brief summary of my presentation. I presented kinetic misalignment where the rotation of the action field produces action dark matter. And the action dark matter with a decay constant much smaller than the prediction of the misalignment mechanism is possible. I also present axiogenesis, where axial rotation produces baryon asymmetry universe, and we obtain a relation between BSM parameters and the decay constant. And actually, this axial rotation can have more cosmological roles, which I briefly introduce here without explaining much. So this axial rotation, if we combine with superstring theory, can lead to the kination domination, the domination of the universe by the kinetic energy of the axial rotation. So in such a scenario, because now the expansionist universe is altered in comparison with the standard radiation domination, it changes the possible primordial gradation wave spectrum that is sensitive to the expansionist universe, such as that from inflation or cosmic stream. So in particular, this leads to enhancement of gradation wave spectrum. And I have just posted the paper to archive that claim that the cosmic perturbation of the cosmic perturbation universe imprinted in the CMB spectrum can be also explained by the axial rotation and its small fluctuation imprinted during inflation. And it turns out that this scenario predicts the local non-galaxianity in the CMB in the cosmic perturbation, like in the Caboton scenario. So if you are interested in, please read the paper or invite me or my collaborators to the seminar. Okay, that's all. So it seems there are many possible cosmological role of action rotation. So maybe more. So it'd be fun to think about that. Okay, thank you.
Thank you very much, Keisuke. It was very nice talk about axion rotation. Are there any questions? We have times for questions. Any question?
Can I ask some questions?
Yeah, Kyu-jung, go ahead.
In your model, are there any problems with isocurvature perturbation or domain walls?
So indeed, so if the inflation scale is sufficiently large, so there will be some isocurvature perturbation. So like, for example, if we consider chaotic inflation, we will have a problem. But the one thing I should notice in this scenario, we start from the huge initial field value of the action radial direction. So then, as pointed out by the Linde, so this suppresses the fluctuation in the angular direction because of the huge radial direction. As you may know, this fluctuation of the angular direction is given by the ratio between Hubble scale during inflation and the initial field value. So this significantly relaxes the isocurvature constraint than I would expect. But still, if we consider a chaotic inflation, we will have isocurvature problem.
So, I feel like during the rotation, the axion field experiences some nonlinear potential. I feel like it is highly dependent on the initial conditions. So, there might be more serious problem with the isocurvature perturbation. I'm not sure.
Non-linear.
So,
I agree. Yeah, indeed. So this angular direction. So I agree. Yeah. So here, this angular velocity is much larger than the Hubble expansion rate. So that indeed enhance the isocurvature perturbation, even at the long wavelength mode. So we may need to give a large mass to the angular direction during the inflation. Yeah, by the more higher dimension operators.
Okay, thank you.
Yeah, thank you. Yeah.
Any other question to Keisuke?
I have a short question. Thank you for your nice overview. It's interesting, kind of interesting avenue for new physics. So you discussed about QCD action case and used the electrolytic transition temperature to be a free parameter, right? And what kind of new physics model do do you?
So that
don't
one
mind.
very toy model would be the cup introducing some singlet field that couples to the Higgs. So for example, we can introduce like this type of coupling. H is a Higgs, and phi is a singlet field. But appropriately choosing the parameter, we can achieve this type of cosmological trajectory. First, Higgs explains the phase transition, and as the temperature cools, the Higgs reacts to the minimum as small as the electric scale. That's one example. But yeah, I want to see if this can be achieved in more, not toy model, more realistic model like next to MSSM. But I'm not sure. Yeah, I really want to construct the express model. Yeah, very motivated express model. Yeah.
Okay. So, and another question is about the action quality problem in the presence of explicit PQ breaking term that you introduced. So, do you make certain assumption about the action quality problem? Yeah.
Indeed, so that gives a lower bound on this index n. Like this n should be, assuming that the separation scale is Planck scale, this n should be something like 10 or 11. So that's the assumption we have to make. But that's anyway assumption we have to make for any QC reaction theory.
Okay.
But yeah.
I see. So it doesn't matter much for the, even if you take the high order, sufficiently high order PQ breaking term, it may be safe. The action quality.
That's certainly a very strong band on the theory. Yeah, like 10. Yeah.
But you could have maybe large effect. I don't know what is value of the initial field value of the radial mode, but maybe if you take the higher, if the power of the PQ breaking term is higher, you need to make the initial value for the radial mode to be very high, right? To get
like GAT scale also. If we take the Kato scale to Planck scale,
Okay.
Thank you very much, Keisuke, for nice discussion. So I guess that's the end of this session. Let's thank all the previous speakers of this session. Thank you. Hyunmi, is there any last minute announcement for tomorrow or tonight?
Yeah, thank you for the participation for today. I think until this late time, and let's tomorrow we'll have another session for dark matter. So please come to join us tomorrow, and see you tomorrow again. Okay.
Yeah, 9:30.
9:30 in Seoul time. Yes.
Yeah.
Okay. Thank you.
Okay. Bye-bye.
Bye.